If this card were to be flicked, what exactly would happen? Is it possible to predict what happens? Luckily, yes. Newton's first law states that objects will keep their current velocities unless compelled to change their velocities by an external force. At the moment, all three objects here have a velocity of 0, so Newton's first law says that they will stay at rest unless an external force acts upon them. Luckily for us, an external force is about to be applied to this card, causing it to fly off in this direction. What will happen to the other two objects as a result? Again, Newton's first law tells us that objects at rest prefer to stay at rest unless acted upon by an external force. In this case, there is no external force acting on the cup or the penny, besides a negligible friction force, so that means that both objects should roughly stay at their current position. With the card gone, there is no normal force to cancel out gravity on the penny. This tomato currently has no velocity, it is at a standstill. According to Newton's first law, it will remain this way until acted upon by an outside force. And that's exactly what happened. The outside force in this case is the hand, which supplied an outside force to the tomato, causing it to accelerate to its current speed. This has been Newton's first law. Newton's second law states that the total force acting upon an object at a point in time is equal to that object's mass multiplied by its acceleration. This can be seen in this demonstration. As you can see, the tomato is completely still. It is at equilibrium. Why is it at equilibrium? Shouldn't gravity pull it down? Yes, gravity is applying a downwards force to the tomato, but the tomato is resting on my hand, which is applying a normal force that cancels out gravity. When I release the tomato, what will happen? With the hand gone, the normal force disappears. To calculate the force of the gravity vector, we can use Newton's second law and multiply the tomato's mass by the gravity's acceleration. This gives us a force of 0.98 newtons. Is the cup accelerating, decelerating, or staying at a constant acceleration? At first, it seems that the cup is moving at a constant speed, therefore it's not accelerating. If this were the case, then I wouldn't have to put any energy into the string to keep it moving, via Newton's first law. I am putting energy into the string, so something is happening that we're not taking into account. You might notice how the cup is always changing direction, and this is because I am always accelerating the cup in a new direction. You can imagine if this cup was heavier, but I used the same amount of force, the cup would go slower. This is because the cup's mass would have increased, meaning the acceleration would have to be smaller in order for their product to equal the same amount of force as before. This has been Newton's second law. Newton's third law states that for every action, there is an equal and opposite reaction. While this might sound vague, it's quite simple. When you want to jump, you push downwards on the floor. The floor exerts a normal force on you equal to the amount that you push downwards on it, causing you to accelerate upwards. Another example of this is this toy car. The car's tires exert a force on the table in this direction. The table is heavy, so the force does not affect it. However, the same force is applied in the opposite direction on the car because of Newton's third law. The car is much lighter, so this force actually affects the car, causing it to go forward. This has been Newton's third law.